Good to see you all. Thank you for being here. So I've been involved in work package 3. I'm a statistician. I work in the maths department in Aberystwyth. And yeah, I've been part of this work package 3 on species distribution modelling. So coastal ecosystems are being modified, and this potentially has an impact on migratory birds, where, as we've heard, there are significant population decline over the last few years. So somebody gave the figure of a quarter of the birds being in the UK. I'm glad that's within my range. Apparently we have between 19 and 27% of the world's curlew population. Habitat degradation and loss is driving curlew decline. So what I'm going to present is a piece of work starting from the national scale, where we look at Earth observation data, particularly Corinne, for different land cover use, and then Paul will bring it down to a more focused site-specific level. One of the challenges is that when we look at the data from Corinne, within the UK and Ireland, there are 37 different land cover types, which is quite a lot in a model. So one of the challenges I'll address is how we reduce that to a smaller set. Right, we've heard the word species distribution modelling quite a lot already. I realise that not everybody is an expert on species distribution modelling, so I thought I'd give you just a little bit of an idea of what we mean by this. So a species distribution model, as the name suggests, is attempting to model where the species are at particular times and under different conditions. So we look at environmental variables, which might include land cover, it might include climate variables, and try and relate what's going on environmentally to where we see the species. And I'm going to focus on curlew for this piece of work. So species distribution models can inform conservation decisions if we've got a better idea of which habitats are being used at different times. Potentially that can have an impact on conservation efforts. And then in some cases, it's possible to extrapolate from a given data set. I've got quite a long data set in this study where we go from 2003 to 2019, and then potentially we can extrapolate to the future to see what's going on. And this can potentially help assess the impact of various human activities on key habitats for the species under study. So, I've got records, as I say, 2003 to 2019, focusing on the wintering population. So we're looking at November, December, January, February, across all those years. It gives us 66 months worth of data. I've used a technique which is called logistic generalized linear models, which basically means that your response, the thing that you're interested in, consists of zeros and ones for whether or not there are curlew observed in a particular month in a particular square in your model. So one of the things that I put into this was information from Corinne. So we've got these satellites. We've heard a bit about that from Walter's talk, and these Corinne data sets are giving an indication of the different types of land cover across all the parts of the UK and Ireland. So I use 3 data sets. There's a 2006 Corinne data set, 2012 and a 2018. And I use that as the center point for a set of years within my study. So 2003 to 2008 was all focused on the 2006 Corinne data and so on. So those are the land cover variables, giving us the percentage of estuary, the percentage of intertidal flats, the percentage of port areas or whatever, all these different variables. So we've got the land cover classes from Corinne, and as I've said, there are 37 variables, quite a lot. We've got some climate variables, both from the Met Office in the UK and Met Iran in Ireland, that Walter put together. And then we also included DTM, so a digital terrain model, a model giving the height of different parts of the country, and slope variables as well. So Warren, who's not here, is a postdoc who gathered a very big data set from all sorts of sources, so eBird and British Trust for Ornithology and the Web Survey, lots of different data. So that was then converted into a 1 kilometre by 1 kilometre grid across the whole of UK and Ireland. So for each month, we've got a yes, no, a binary variable as to whether curlew were seen in that month or not. And now, zeros don't necessarily mean there aren't any birds there. We had a long discussion about this. They're cryptic species. It's difficult to see the curlew. So if there's a 1, we know that something was observed. And if there was a 0, either there are no birds or there are birds and they weren't seen. So we've made that very clear in the way that we've written this up. As I say, we've got 66 winter months. So it's November, December, January, February, 2003 through to 2019. So we took those 37 land cover variables and I applied a filtering process. Doesn't really matter what it is, but it's called cross-validated lasso. So we have a filter which reduced it to a much smaller set of land cover class variables. And we'll see that it's quite interesting that we can pick out which habitats the curlew are using during the winter months. But the climate variables and the digital terrain model, those were included in all of the final models. What we've got going on here is we've got the Corinne land cover classes that ended up featuring in our models. So already it's a reduced set, 1, 2, 3, 4. We've probably got about, I don't know, 15 or something instead of our 37. And then we've got the different months, November, December, January, February, and then the 3 Corinne data sets, 2006, 2012, 2018. My main take-home message from this is that with the exception of February, where lots of variables are still included, only a few of those land cover variables are needed to explain a reasonable amount of the variability. And if we look at which ones have come up, estuaries, intertidal flats, salt marshes, beaches, dunes and sands features quite prominently. There's quite a lot of coastal information coming out of these models once we've applied the lasso filter. Here are some results where we can see the 2018 Corinne window. The red and yellow ones is the means across the 6 years in each of those windows, and the other one gives some measure of the variability. And we can see that there's quite a prominence of these coastal areas. You can see the red dots are kind of towards the coastal areas. So the coastal areas seem to have emerged as significant in these wintering populations for the curlew over this period. So just a few model diagnostics, something called the area under the receiver operator characteristic curve. They're high numbers. We've got good numbers, so it's reasonable fit for the models. So let me just recap what we've done. We set out to model the distribution of sightings of overwintering curlew over this 15 or 16 year period. We had a big observational data set, public access and request only data. We included land cover variables. We included some climate variables, including things like the number of frost days, the number of days below a 5-degree threshold, which was part of Catherine's PhD. And we also had the digital terrain model. And then we were trying to model the observations of curlew over those months. We had this filtering step that reduced the number of land cover classes that ended up in the models. And the coastal habitats emerged quite prominently in the results, quite consistently across the whole of the study. The receiver operator characteristic curve showed a good model fit, and it was a robust selection of a small selection of explanatory variables using cross-validation and multiple random seeds in my computation in the code that I wrote. So it seems from this that we've got evidence that curlew are using quite specific sets of habitats over their wintering distribution. Estuaries, intertidal flats, salt marshes, beaches, dunes and sands, and port areas, which is probably somewhat artifactual, but nevertheless, port areas is probably a bit of a proxy for coastal regions. Those feature prominently. And then we saw that the February distribution seemed to be a bit more complex. You seem to need a wider diversity of explanatory of land cover classes to try and explain the distribution in February. And maybe the curlew are preparing for migration, making short journeys up and down the coast and kind of engaging with a wider range of land cover and a wider range of habitats. So I've talked about the national scale, so UK and Ireland are considered as a whole, and now Paul's going to zoom in to a more local scale. So I'll pass over to you, Paul.
Thanks, Kim. I'm gonna start with a quick exercise, and if we can all just briefly shut our eyes and picture a landscape, and that can be any landscape. Kind of what's the first thing that comes to mind when we consider what that might be? For me, that's what a landscape looks like. I work in computers, and to me, it's all squares and grids. But we probably had a range of different things. We've seen a load of different photographs and a load of different images from today, looking at all of the different estuaries, all of the different wild landscapes and natural landscapes and urban landscapes that these birds utilize. And the important thing why I mention this is because for the work that we've been doing so far, we've been looking at the Korean land covers at a 1 kilometer scale. And the land cover variables that we incorporated in the models that Kim's just presented has been percentage of that land cover. That could be percentage of a salt mass, percentage of arable land, percentage of improved grasslands. But when we're talking about this at a case study or a landscape level, it's important to note that actually landscapes come in various different shapes and sizes. And actually the percentage of a land cover might not be necessarily the best feature to use when we're talking about specific case studies and specific estuaries. And in that instance there, you can see that all of those landscapes have the same proportion of those two different land covers, but they're wildly different configurations representing quite perhaps different complex, or actually even in a sense it's quite simple, it's just two land covers, different landscapes. And so the case study work that we've been using has been looking to say, can we improve the models beyond just the simple percentage of that land cover? And so, yeah, in our national models, they would all be represented the same, even though we probably quite are confident that they'd be representing quite differently. Now, going back to that first exercise, I asked you what a landscape was. That's often quite one of the challenges when we're dealing with ecology, because we're not actually interested in what we consider to be a landscape, but what a Curlew considers to be that landscape. And so Curlew perhaps are interested in what the percentage of that landscape is for different land covers, but there might be other features, particularly when we're talking about a very local scale, a very kind of in the moment lived experience of those Curlews, what might actually be important. And again, this is just very simple. What is green? Is it grassland? Is it salt marsh? Is it mudflat? Again, once we start adding more variables, more land covers into the mix, it becomes increasingly difficult to parse out those differences. So looking at ways of moving beyond just simple percentage land cover, which I should add is pretty much the status quo of how we do this. Any type of modeling at a national level, even at a regional level, is dealing with percentage land cover because of the computational costs required to represent that. So the question we've been asking for the case study is feeding into the movement data that we've collected, the habitat data that the water's captured, and looking to see if we can apply a species distribution modeling approach at a very fine scale resolution, asking that question, can metrics representing that spatial configuration of the landscape improve species distribution models? Now, what do I mean by landscape metrics? Now, there's a wide range of different metrics out there. There's lots of different equations. I went a different route to water and decided not to show any equations today. But if anyone wants to nerd out, I'd happily kind of go through it. And Luke did his master's thesis on it as well. So he loves talking about landscape metric equations. But you can see that one in the top left there, planned. That is percentage land cover. That is what I've just been talking about. And this is improved grassland in Ballyteague. And you can see just the challenge that we get when we go to Ireland, that actually the whole of Wexford is improved grassland. You're not getting much variation at a 1 kilometer resolution. Most of that area is going to be grassland. So we're looking for ways of perhaps teasing out more nuance. And you can see just some of the different ones. LPI is largest patch index. That's the value between 0 and 1 that's talking about where the largest patch of that specific habitat type is. Plaid J is proportion of like adjacencies. It's dealing with connectivity. How connected is that area? Contiguity is another connectivity metric. And fractal is dealing with edge effect. And so how much edge, how much perimeter of these different land covers, basically how distinct is it and all of that. And so you can see from those 5 images, we get 5 very different representations of what that landscape is looking like and what that might mean in our models. And so we applied very much a similar approach. I didn't use the lasso penalization, but we used all of these different methods using the tagging data that Catherine talked about earlier as our input data, filtering out the different observations such that we've only got 5 observations per recording period. That's either 24-hour period or the day or the night. And we used the 10-meter habitat classifications that Walter talked about as well with those different things. And you can see that the key there is the different reds, and that's presenting the most accurate model that we can talk about. And what we're seeing is largely speaking, we're seeing improvements in the model performance when we consider these landscape metrics beyond just that proportion of that land cover, which is quite important really. We're saying actually, yeah, the percentage of land cover gets us so far, but we can improve those numbers. Now they're small differences, but they're important differences, and particularly when we start to look at the different importance of those different variables and what variables are coming into the different map, that becomes quite key there. So yeah, it's the importance of landscape metrics is very prominent for Ballyteague, and again, we've already seen some reasons why that is. They're using a much larger array of habitat. The points are going a lot further, they're going a lot inland. It's less so for the dovey, but it is still in there. We can go into the different accuracies and how we need to consider multiple ones, etc., etc. I'll try not to do that now, but it's perhaps a little bit more nuanced. And again, that's based on what we've been seeing, whereby we have a lot of points within, or the birds aren't leaving the estuary. So the estuary is playing a much larger role in terms of what we're looking at here. So I've just put a couple of maps here. That is Ballyteague, and you can see the differentiation between the night and the day. So we can pull out those different diurnal patterns. Catherine mentioned that island, that we can really see that's coming out in our metrics based on those different habitats. But particularly when we go inland, and again, I have a slide sometimes where I flick back and forth, but I hope we can see the differences in those fields that are going inland. They are different fields. They're using different fields in the day compared to the night. And particularly in the night, they are avoiding areas where there is a connected area of forest or woodland and a connected area of builtland. So they're not necessarily avoiding those locations in the day, or perhaps not as much as they are, but they're using areas where there might be one building or two buildings or a certain amount of buildings or a certain amount of trees, but aren't representing those conglomerates of those areas as well. And again, we can posit that's perhaps due to predation, but there's interesting differences in there in terms of they're not necessarily avoiding the individual buildings, but they're avoiding the villages and they're avoiding the towns. And again, if we think back to the percentage, we could have a scattered building distribution, which we certainly do have in Ballyteague, but they're not necessarily avoiding those individual houses, those individual farms. They're avoiding the towns, they're avoiding those larger areas. And the same with the woodlands. They're not avoiding smaller areas of trees because they're perhaps not as suitable for the predators that might be there. So that's quite an important distinction. We do get that diurnal difference for the dovey as well, but it's perhaps less clear. And again, we are seeing them predominantly on the estuary there as well. So that's quite, and I still need to kind of extrapolate this up now to Kefni. It takes about 2 weeks to run the landscape metrics on the computer. So that's why it's not widely done, but it's done on the computers. And again, that just unfortunately hadn't finished. But yeah, the kind of results, it's quite key because we're seeing not just larger areas of salt marshes, but connected areas of salt marshes, connected areas of improved grassland and semi-natural grasslands are important, particularly in Ballyteague. And I've talked about that differences at the night, where at night the connected salt marsh and semi-natural neutral grassland is still important, but again we're seeing that more predominantly in Ballyteague than the dovey. In the dovey, we're seeing a much less prominent role of the grasslands. But again, that's not to say that it wouldn't necessarily be important come some of the projections that we're going to see in the future, where we might be getting sea level rise. There might be a bit of coastal squeeze, and the role of those surrounding areas becomes a little bit more important as well. But ultimately as well, we've now developed a tool whereby we can extrapolate these relationships to look at how habitat change might work. So we've heard already about some of the different management strategies. What happens if you do locally flood an area? What happens if you do remove a hedgerow? What happens if you do plan for afforestation? We can plug those projections into our maps and see how that impacts it. And again, that becomes important because you're not just removing a percentage, you're not just changing the percentage of a land cover from 2.5 to 2.4, you're all of a sudden, you're completely changing that spatial configuration. So that strategic placement of that hedgerow or removal of that hedgerow might increase the connectivity and all of a sudden make two fields completely suitable, whereas before it wasn't, or vice versa. That we're seeing a lot of kind of the drive for hedgerows in carbon, a drive for forests for the carbon capture, but actually the strategic placement of that within the coastal regions and within that coastal distance, that's quite important. And we've developed a tool there that we can implement this methodology now to assess how that impacts the spatial configuration across the road. So thank you very much for listening, and we'll move on.